Chapter 7, Probability and Samples, the distribution of sample means. There will usually be a discrepancy between the sample mean, which is denoted by M, and the true population mean. We recognize that if we take a sample from a population, that the sample statistic won't always be identical to the population. In fact, it's rare that it would be identical. We expect some difference. This discrepancy or difference is referred to as sampling error. The amount of sampling error varies across samples and is related to the size of the sample. And again, we recognize that larger samples are going to be more representative, therefore decreasing the error between M and mu. Smaller samples will be less representative and therefore increasing this discrepancy. The variability of sampling error is measured by the standard error of the mean, and the equation we learned is standard error of the mean is equal to standard deviation of the population over the square root of n, and we've discussed in detail the relationship between the sample size and the standard error. Again, as n increases, the standard error of the mean decreases. If the standard error of the mean decreases, that means the error or sampling error is also going to decrease. We'll have less discrepancy between a sample statistic and the population parameter because a larger n is more representative. The sample will look more like the population because it's taking more x values to compute m. Again, m is the sum of x over n. So if we have more x values in our sample, they are more representative of all the possible values in the population. Figure 7.7 is a good example of a typical distribution of sample means. At the beginning of this chapter, we introduced the idea that it is possible to obtain thousands of different samples from a single population. And we worked with a very small population of 4 scores to illustrate the construction of all possible samples. In that case, there were 16 different possible samples and therefore 16 different sample means. And this idea is applicable to any population. Each sample has its own individuals, its own x values, its own scores, and its own sample mean. The distribution of samples mean provides a method of organizing all the different sample means into a single picture. In this figure, we show a typical distribution of sample means to emphasize the fact that the distribution contains many different samples. We have constructed this figure so that the distribution is made up of hundreds of small boxes. Each box represents a single sample mean. So for instance, this little box over here is representative of one sample, as is this little box. Again, each sample mean is derived by taking the sum of x for that sample divided by n. Similar, if that sample over here in red is the sum of all those x values divided by its sample size. And again, we can look at this sample here, and m would be the sum of x over n. I use different colors again just to show that these are 3 different samples. They produce 3 different sample means, and we see where they would perhaps reside in this overall distribution. We could just put it down here at the bottom of our x distribution to better understand where it resides in relation to the population mean. But it's a wonderful graph for us to better understand what we're doing when we talk about the distribution of sample means. Each little box is representative of its own m value, its sample statistic, and is derived by taking the sum of x values and dividing by how many we had in that particular sample. We should notice that the sample means tend to pile up around the population mean. Again, this is forming a normal distribution and is predicted by the central limit theorem. That here we have frequency, right? Frequency is denoted here. Therefore, the highest peak, now I'm going to erase all of these little colors here. so that you get a sense of the number of samples that are congregating around the population mean. And I didn't draw that very symmetrically, but notice how many are concentrated in that center opposed to how many are in the tails. Gives you a sense of how rare those sample means are in comparison to the ones in the center. We have much higher frequency in the center here, and the majority of the scores are in the middle, congregating around the population mean. This figure provides a concrete example for reviewing the general concepts of sampling error, the natural discrepancy between a sample statistic and a population parameter, and the standard error, which represents the average difference between M and mu, the sample mean and the population mean. Although these points may seem obvious, they are intended to provide you with a better understanding of these two statistical concepts. So first, sampling error. Again, the general concept of sampling error is the sample typically does not provide a perfectly accurate representation of its population. More specifically, there typically is some discrepancy or error between a statistic computed for a sample and the corresponding population parameter. As we look at this figure, you should notice that the individual sample means are not exactly equal to the population mean. So here, this group of samples, all of these in the middle, are identical to the population mean. But we see that all these other, again, all of those boxes would have means. Let's just say the mu is equal to 50. And we would say that all of those M values are equal to 50, right? And there are multiple of them, and they're all identical. But notice all of the other ones that aren't in that red zone that are not identical to the mu. So in fact, we have 50% of the samples are greater to the right of mu. So that would be all of these values, all of these boxes of our representative sample means that are different from mu. And we have on the lower end all of these sample means. Again, each box represents a sample mean, and these are not identical to mu. The only ones that are identical to mu are that highest column there in red. We'll call it the red zone. Everything else includes what we refer to as sampling error. The natural discrepancy between a sample mean and population mean. It's just by chance that we construct a sample, we compute the mean is equal to sum of x over n, and it generates something different from mu. And again, we anticipate that, but we also recognize that in the center values, if we go back to what we learned in chapter 5 about the common region, one standard deviation unit, well, in this case, we can think of one standard error unit as being representative of values close to the mean. So again, I had drawn that earlier. So we may say this is one standard error unit above and below the mean. And all of these are not identical to the mu, only that center value, again, I'll put it in red. Only this center value are values equal to the mean, but everything else is similar enough where we would consider it to be equal to the mean. Again, it's not identical, but similar enough where we say that these differences are simply as a result of sampling error. Again, the standard error is representative of the average difference between any sample mean and the population mean, or what we would expect. We often refer to standard error as representative of the expected difference between M and mu. So again, these in this rectangle would be considered relatively representative of the population mean, but we have some values out in the tails, right? So let's say this one, this sample mean is very different from the population mean. Similarly, if we talk about this sample mean over here, different from the population mean. So the standard error again is taking into account all the differences. So we have some values are very close. Let's say this one, very close to mu, whereas we have this other one very far out in the tail that's very different. So the standard error is simply representing the average distance or difference that we see between m and mu. So again, standard error represents the average difference, difference between m and mu. So each one differs a certain amount. Collectively, standard error represents the average difference, and sometimes it's referred to as the expected difference between m and mu. So knowing the standard error gives researchers a good indication of how accurately their sample data represent the populations that they are studying. Let's use this to talk about the example of SAT score. So we had in a previous video been given an example where the average SAT score was equal to 500 and we had a standard deviation equal to 100. When we construct the distribution of sample means, the mean of means is equal to 500 and the standard error was equal to 20. And that's if we were using sample sizes equal to 25. So let's say we are going to engage in inferential statistics again to determine if a sample that is exposed to treatment is significantly different from the untreated population. So here we have the construction of a distribution of sample means. Let's say this is the mean of means is equal to 500 in the center. And we know that the standard error is equal to 20. And if we took a sample of 25 individuals and they were exposed to intense SAT curriculum, a program that helped them improve their SAT scores, and after, let's say it's a 10-week program of intense SAT training, and after the program, their sample average, so they take the SAT test after this course, and their average is equal to 600. So again, we took all of those 25 individuals and we divided by, we took the summation of all of their individual SAT scores and divided by how many we had, and we got a sample mean of 600. Now we know that 600, if we were to convert that into a z-score, z is equal to m minus mu divided by standard error. Z is equal to 600 minus 500 divided by 20. Z is equal to 100 divided by 20. And we get a very high z-score equal to 5. Which would place us way over here. So let's say this is 600 equivalent to a z-score of positive 5. And then what we would do is ask ourselves, what is the likelihood of randomly selecting 25 individuals from the population that did not go through this intense training? Again, that did not receive the SAT training course. What is the likelihood that they collectively would generate a sample mean of 600? Given the visual here, it would be very unlikely because, again, the most representative sample means are here in the center, one standard error unit above, and this is 5 standard error units above the mean. So if we're relating it back to the untreated population, yes, those samples do exist in the population, but they exist in small numbers. So the likelihood of just randomly selecting 25 individuals from the population and that they would yield a sample mean collective statistic of 600 is very unlikely. So again, this lends itself to support the hypothesis that the SAT intense course is effective. that we are generating the sample mean not due to chance, but more likely due to the fact that these 25 individuals collectively received this intense SAT training. So hopefully this gives you a better sense of how we're going to use the distribution of sample means and probability to draw conclusions about a hypothesis. Any values that are centered around the mu are considered very similar to the mu and do not give us the information necessary to support a hypothesis, as in this case that the intense SAT course is effective. In other words, if after receiving training, let's say those 25 individuals, after they received training, their collective SAT score was 510. So yes, it's different from the population. It is higher, but it's not different enough for us to conclude that the treatment is effective, because the probability of obtaining this value, right, the probability of selecting 25 individuals randomly and that they generate a SAT average of 510 is pretty high, because again it's following that rectangle, the area of high frequency, of high probability, and therefore we would conclude that the treatment most likely was ineffective, because the score of SAT score average of 510 is very similar to the population of untreated individuals, the regular SAT distribution of scores. Figure 7.8 demonstrates the use of standard error and provides additional information about the relationship between standard error and standard deviation. So a recent survey of students at a local college included the following question: how many minutes do you spend each day watching electronic video? For example, spending time online, watching television, cell phone, the use of an iPad or tablet, etc. The average response was 80 minutes, and the distribution of viewing times was approximately normal, with a standard deviation equal to 20 minutes. So this is these are the parameters that are given. So they said 80 minutes on average, with a standard deviation equal to 20 minutes. And the distribution was said to be approximately normal. Next, we take a sample from the population and examine how accurately the sample mean represents the population mean. More specifically, we will examine how sample size affects accuracy by considering three different samples. In the first graph, graph A, n is equal to 1 student, and then B is in reference to a sample size of 4 students, and C is in reference to a sample of 100 students. So in graph A, if we're constructing a distribution of sample means, we know that the mean of means would equal mu, so that's 80 here, so it would still be 80. And then the distribution of sample means, its standard error is equal to standard deviation over the square root of n. And here we're saying that n is equal to 1 individual, 1 student. So the standard error of the mean is equal to 20 over the square root of 1. And our standard error of the mean is equal to 20, which was the original standard deviation. So in other words, when n is equal to 1, the standard error of the mean of distribution of sample means will equal the standard deviation of the population. So when the sample consists of a single student and a single x value, the mean for the sample equals the score of that student. In other words, m is equal to x, because there's only one of them. Thus, when n is equal to 1, the distribution of sample mean is identical to the original population of scores. In other words, we're just recreating the original population because n is equal to 1. And consequently, as I stated a minute ago, the standard error of the distribution of sample means will then equal the standard deviation of the population. We should also notice that the original distribution was said to be normal, which is why graph A, B, and C are all normal distributions. But notice the shape. The variability is denoted by the spread of each of these graphs. So in the first one, our sample size is the smallest. It's equal to 1. Then we move to B, where the sample size has increased to 4. Notice that the range of scores and the variability denoted by the standard error has decreased. And similarly with C, N has increased to 100, so the standard error is even smaller. So for B, our sample size is equal to 4. Again, the mean of means would equal 80 because mean of means is always equal to mu. And the shape is normal, and the standard error, the variability, is calculated by taking the standard deviation divided by the square root of n. In this case, it would equal 20 divided by the square root of 4, and we get 20 over 2, and we get 10, which is why we've expressed it here. Notice again, as n increased, the variability decreased. And then finally, in graph C, we see that n is equal to 100. Therefore, our standard error of the mean is equal to standard deviation of the original population, which was 20, over the square root of 100. So we get 20 over 10, and our standard error is equal to 2. So again, as n increased, standard error of the mean decreased. In short, this example demonstrates that the smallest possible sample, when n is equal to 1, the standard error and the population standard deviation are the same, as we saw here, right? The standard deviation, standard error of the distribution of sample means is equal to the standard deviation of the population. When the sample size increased, the standard error gets smaller, and the sample mean tends to approximate mu more closely. In other words, the samples that we're drawing are going to be congregating closer to the mu in the center. Notice the peak is higher, so that's representative of more values centered around the population mean. Therefore, the standard error defines a relationship between the sample size and the accuracy to which the sample mean m represents mu. So again, here we see an even higher concentration around the population mu. And again, this relationship is important because as variability decreases, the difference between the population mean and the sample mean, the sample that receives treatment, the differences become more evident, or they're easier to detect, I should say. If the sample that receives treatment is congregating around the population mean, then the treatment was ineffective. But if it is significantly different and the difference is established by this average, right? The standard error of the mean is the average expected difference. If it's way or well outside of that range, then we have reason to believe that the treatment was effective. And we'll end this lecture video with a brief introduction as to how we would expect to see standard error expressed in a journal. So journals vary in how they refer to the standard error, but this is the most common notation that you would see, either SE or SEM, so standard error or standard error of the mean. It's often reported in a table along with N and M, so the sample size and the sample mean for the different groups in the experiment, as I will show in the next slide. And when we add a graph, it gives us a visual sense of differences. Again, the researcher is hoping for large mean difference. We have the untreated population mean. We take a sample, we expose it to treatment. We certainly don't want that sample mean to equal the population mean. We want it to be very different. Again, visually speaking, the untreated population mean here. If we have treated sample means around here, that means that the treatment was not effective. But if we have sample means out in the tails, then we say something is happening. Something what resulted from those individuals receiving or being that were exposed to the treatment. Figure 7.9 illustrates the use of a bar graph to display information about the sample mean and standard error. In this experiment, two samples, groups A and B, are given different treatments, and then the subject's scores on a dependent variable are recorded. The mean for group A is equal to 15, denoted here. So the height of this bar is representative of the mean of that group. And for group B, the mean is equal to 30. So the height of this bar, so that's representative of the mean for each group, group A and B. For both samples, the standard error of the mean is equal to 5. So they're equal in standard error, and then it's represented by these brackets. So for this group, the average difference between the sample means and the population mean for this group extends from 15 to 10 and all the way to 20. And for the other group, again, standard error is also equal to 5, so the average difference extends from 25 to 35. Now visually, again, our purpose of doing research, especially when we have two different groups perhaps exposed to two different treatments, is to see if they yield different results. Now again, we know that the mean for the first group is equal to 15, and we know that that is different from the mean of 30. But we can't base our conclusions strictly on the mean. We also have to take into consideration the average difference that we would anticipate for a sample drawn from each of these groups. And the standard error represents that visually for us. So again, this range for group B extends from 25 to 35. And that does not overlap at all with this group A. The standard error extends from 10 all the way to 20, including the mean of 15. So visually, we don't see any overlap in those values. Again, what I mean by overlap is this, if we extended this line over here, that's not including the mean of the other group, nor does it include that average difference range that we refer to as the standard error. If we were to think of this using a graph, a normal distribution, and let's say this is group A, and their average was equal to 15, with a standard error equal to 5 points. And so if we went up 5, that would take us to 20, and then another one 25, and then another one 30. So let's plot 30 here, and that's representative of the other group's distribution mean of 30, and also going up and down one standard error unit. And notice again that these means are different, but one standard error, again, this takes us to, and I'll put that in black, this takes us to 20. And on this end, it would take us to 25. So there's no overlap, meaning that we're seeing a difference in these two groups after treatment. If, for instance, let's say group B didn't have an average of 30 as it's indicated here, and let's say instead it had an average of 20. So again, for the first group, the average is 15, and let's say the second group, we'll make this up, was equal to 20, and then we would see overlap. Again, this way would take us to the value of 15 for the one standard error unit for the second group. And notice now these groups, the distributions are overlapping. This is just another visual interpretation of these bar graphs that we see to the left. And so if they're overlapping, then that's demonstrating that the average difference that we'd expect extends into the average difference of the other groups. So they are overlapping and therefore illustrating that there's no difference. Whereas in this illustration, we see a difference, that they're not overlapping even when we extend out one standard error unit above and below. So this is one visual interpretation that you may be exposed to. And here we have another experiment, group A and B, and it's a sample of individuals, and they take an assessment 4 different times, and the dot represents the mean of that trial, and then the brackets represent the standard error. Again, because we don't see any overlap, we would conclude that these groups are distinctly different. They're performing differently If the brackets extended into the other area, what I mean by that, if the standard error here extended further for both trials, then we would say that there isn't a significant difference, but that's not what we see. Instead, we do see that there's separation and that the standard error is expressing no overlap, and then we would conclude that there are distinct differences between these groups that were most likely exposed to different treatments. So looking ahead to inferential statistics. Inferential statistics, as I have said many times, use sample data to draw general conclusions about populations. Sample information is not a perfectly accurate reflection or representation of its population. Again, we expect some difference, and that natural discrepancy or difference is referred to as the sampling error. And our job is to determine if the difference that we see between M and mu, right, is it due to sampling or error, or is it due to statistical significance as a result of treatment or comparison of a quasi-independent variable? Differences between the sample and population do introduce uncertainty into the inferential process. That we use probability to draw inferences from sample data. We recognize that probability isn't saying that everything is 100% certain. Probability refers to proportions or percentages, likelihood of something happening, and we would never expect the likelihood to equal 100%. But again, when it comes down to it, our job is to determine, is the sample mean different from the population mean because of a natural discrepancy that we anticipate, sampling error, or is it because the treatment was effective? In the next video, I'll walk you through the process of inferential statistics using sample data that would lead us to developing a foundation for the technique known as hypothesis testing, which is introduced in Chapter 8. So we'll use an example to go through the step-by-step process to draw conclusions regarding a hypothesis. So that concludes this part of Chapter 7.